In section 6.6, we're going to continue to build upon this idea of revolving, but then we're also going to throw in what we just learned in 6.5 about arc length to come up with this new formula that involves integration for finding surface area for surfaces of revolution. So this is a little bit different than what we did in section 3 and section 4 when we did volumes of revolution. So when we did volumes, we started with an enclosed region, and when we revolved it, it created a solid. So that solid we could calculate the volume for. In this section, we're only going to revolve an arc or a piece of a graph. It's not going to be an enclosed region or an enclosed area. We're just revolving a piece of a graph. So the three-dimensional object that we're going to create does not have volume. It's going to be three-dimensional, but it's got nothing on the inside of it. It's just going to be paper thin, and we're just interested in finding the surface area. So we're going to put together kind of the concepts from our volume by slicing section, and then also the concept for arc length. So let me show you a little picture to start with. If we just have a piece of a graph, f of x, on an interval a to b. Now, this is not an enclosed region. We don't have sides to it. We don't have a bottom to it. It's just a piece of a graph. It's just an arc. And we're going to revolve this about the x-axis for this one. Now, we could revolve around the y-axis as well. And we're going to see two different, just slight variations of the formula depending on what we're revolving around. So if I take this arc and I revolve it around the x-axis, just like before, we'll have, when we get to 180 degrees, we'll have an exact replica when we get to 180 degrees, and then it will come back around 360 and get back to where it started. So it comes down and then goes back. And every point on the graph does that. The difference now is there is nothing inside of there. That is all airspace. So it does not have volume. All it has is this surface. It's just got this surface here. And when we revolve it, it becomes like a three-dimensional surface. And we want to know what is the surface area. So what we're going to do is we're just going to pick a representative point on the edge and talk about what happens to that representative point. So let's just say we take this point. Now, if I take just that one point and I revolve it around the x-axis, it's going to go around, it's going to hit 180, and then it's going to come back. And we see all we have here is a circle. So our representative point on our graph, or on our arc, creates a circle when it gets revolved. And when we do surface area, we're just going around the outside edge of the circle. So for that one thin little slice circle there, we want to know what the outside edge of the circle, what the distance around it is, and that is circumference. So the circumference for a circle, the formula is 2 pi r. That is just one circle from one representative point. So what we're going to do is we're going to extend this out to every single possible point on f of x from the interval a to b and make tons and tons and tons of representative circles. So I can pick another point over here and I can follow it around and get another circle. And I can pick another point over here and follow it around and get another circle. Notice that all these circles are a little bit different. And what's different about them are their radii. Now the radii for these circles, when we go around the x-axis, the radii is just based on the function. We're going from our axis of revolution out to whatever that particular function value is. So for the blue one, the radius of this circle is axis of revolution out to the function, which is slightly different than the pink one. And then for the light blue one, axis of revolution out to the function, which is a little bit longer than the pink and the blue. So for one individual circle, all the way around would be 2 pi r. But then we want to do this for every single possible circle we could get out of that function from a to b. So this function, since it is a curve, and since it has an arc length, we are going to extend this out to 3 dimensions and include the fact that this is not a straight line, but this is a curved line, by also including our arc length formula, and say that we want to find this circumference value for every single circle that could be created between A and B. We want to calculate the circumference of those circles. Remember, for R, we were just using f of x, and we need to do it for every single circle along the arc length of that function. And the arc length formula, remember, is square root of 1 plus f prime of x squared dx. This is specifically what we would use if we were revolving about the x-axis. It is going to change a tiny bit if we revolve around the y-axis. But when we revolve around the x-axis, all we have are these circles. That's where the 2 pi f of x comes in. But we've got a bunch of them that all get situated along this arc length of f of x. So we have to include that arc length, because we want all of them from A to B along the arc length of f. So that is our surface area formula for when we revolve f of x about the x-axis on the interval A to B. It's going to change slightly when we revolve around the y-axis. So before we look at any examples, let me show you what it looks like around the y-axis. So very similarly, we could take a graph or a piece of a graph on an interval from A to B, but this time we're going to revolve it around the y-axis. So when we start to spin it at about 180 degrees, we will have an exact replica of it. I'll try my best. It'll go 180 and then come back around, and every single point is going to do that. So again, there's nothing at all on the inside here. It's completely hollow. All we have is a surface. And if we look at, again, a point on the edge, and we follow a single point around, it's going to make a circle, just like it did before. There's a little bit of a difference, though, in these circles. And the difference is the radius. So the radius is always starting at your axis of revolution, and we go out to the edge of our circle, and we want to know that distance. Now this time the distance is horizontal. So to measure that distance, we're starting at 0, and we're going down to some x value, something in between A and B. And then for the pink circle, we're starting at our axis of revolution, going out to the function, and we're measuring that horizontal distance, which again is some x value in between A and B. So all of these circles are going to have a radius somewhere in between A and B. It's going to be some x value. and we'll actually have a circle for every single value in between a and b. So down here, we have one that's exactly a. Up here, we have one that's exactly b. And since this is a nice continuous function, we'll have one for every single value in between. So the radius for each one of these circles is just some x value in between x equals a and x equals b. Now a and b are going to be used in our integral. Those are the bounds for our integral. So the way that we also use that as our radius is we just have to put an x in the radius spot. So we're still integrating from a to b, but this time for those circles, to find the circumference of one individual circle, we're going to do 2 pi times some x value. So 2 pi times some x value in between a and b. And then at that same x value, we need to also include, we want to do this for every single x value along the arc length of that function. So we also have our arc length piece in there. So the only difference between these two formulas, this is when we are revolved about the y-axis. The only difference when we go around the x-axis, oops, I did not mean to do that. When we go around the x-axis, the radius for each of those circles is the function value. When you measure each of those individual circles' radii, you're going from your axis of revolution up to the function. So the radius is the function value. But when you go around the y-axis and you look at those individual circles and you measure the radius goes from your axis of revolution. It does go to the function, but that length is a horizontal length. And horizontal lengths in the xy plane are x values, not f of x. F of x is a y value. It's a y coordinate. So it's just some x value between a and b. So when we go around the y-axis, all we have to do is put an x there in the radius spot. And that's the only difference. Everything else is the same. We still integrate from a to b. We still have our 2 pi. And then we still have that arc length piece. The only difference is what we're using for our radius function. Here, our radii are measured vertically. So we use f of x, which is equivalent to y, which is our vertical axis. And for this one, we measure our radius horizontally, which is equivalent to the x-axis. So we have an x in there. So let's look at an example for each of them. So we're going to find the surface area. Of the surface that's created when f of x equals, let's say, let's just stick to something simple for now. Let's say x squared on -1 to 2 is revolved about the x-axis. And these, again, very often, once you get your integral set up, they might turn into something that we don't know how to integrate yet. So the important thing is being able to read the problem, understand what you're being asked to calculate, and know how to set up that kind of integral. Once you get the integral set up, we can just plug it into the calculator from there, because these are all going to be definite integrals. So f of x equals x squared, that's our standard parabola. We've got negative 1, 1, 0, 0, 1, 1, 2, 4. So there's the arc. And we're going to revolve that around the x-axis. So after we revolve it 180 degrees, we'll have the exact replica or reflection of it below the x-axis. In between all of the corresponding points, we'll have these little arcs. So there's 180 degrees, and then back around to where it started, 360. So it's kind of a weird looking surface. We've got a point that's on the axis of revolution, so it looks like it gets pinched off there a little bit. That's perfectly fine. Doesn't make any difference with how we're going to do our calculation. So just to kind of reinforce exactly how we're going to do this, if you pick a random point on the edge and follow what it does as it gets revolved, it's just a circle. When you look at the radius of this circle, it's measured from our axis of revolution up to our function. And that radius is a vertical line, which means I need some sort of vertical value at that point. Well, that point on that function, I don't have that exact point marked. It's about 1.5, 2.25. But that exact point on that graph, the vertical height is represented by the y, which is the same as f of x. So for each individual circle, all the way around is 2 pi f of x. And we want to do that for every single point along this curve, or this arc. So surface area is the integral from, we were told, negative 1 to 2. For the individual circles, it's 2 times pi times radius. Our radius here is vertical, so it goes to the function x squared. And then we want it for every point along the arc, so we also have to multiply by arc length, which is 1 plus f prime squared. So we need to work that out separately. Let me do that in another color. So f prime of x is 2x, and then we square it, we get 4x squared. So that's what we want inside our integral there, 4x squared dx. So we could clean this up a little bit. Typically, we'll pull any of the coefficients out. So the 2 pi can just come out front. And we're just integrating x squared times the square root of 1 plus 4x squared dx. And we don't know how to integrate that one by hand yet. So we're going to have to just type that into the calculator. Because it's going to be a calculator value, it is most likely not going to be an exact value. And because of that, we can go ahead and multiply the 2 pi in. If you want to, you can see what you get without the 2 pi and see if it comes out to be a rational number. If it does come out to be a rational number, then you can keep it exact. If it does not come out to be a rational number, then you can go ahead and multiply the 2 pi in. So let's get this into our calculator. So we're integrating from negative 1 to 2, and our integrand is x squared times the square root of 1 plus 4x squared. And the calculator, just for this integration piece, is saying 9.0775. If you want to, you can see if the calculator will change that to a fraction. And that is a way to check to see if it's a rational number. When I ask my calculator to change that to a fraction, it just gives me back 9.0775 again, which means it's not a rational number, it's an irrational number. So we're going to have 2 pi times the 9.0775, So I'm just going to go ahead and multiply the 2 pi into it. So this surface area is about 57.04 square units. It's an area, it's a surface area, so it's going to be square units. And again, because we were going around the x-axis, the radii were measured vertically, so that vertical distance is a y value. And from this function, the y value is the same as the function value. So we plugged a function in for the radius. And then let's look at how it'll be just a little bit different if we go around the x-axis. Let's find the surface area for the surface formed and I'm gonna do something crazy. I might regret it. Let's do sine 2 sine x on 0 to pi over 2 is revolved about the y-axis. No, I think it'll be okay. It's definitely not going to be something we can do by hand, but let's take a look at this one. So the sine graph looks like this. Remember, we call it the sine wave because it just goes up and down forever. The piece from 0 to pi over 2 is just from here to here. So we really don't need the rest of it. We just want to take this piece and revolve it. And we're going around the y-axis this time. So I'm going to start to spin it, and when I get to 180 degrees, I'll have the reflection of it over the y-axis. So I'll go around to 180 and then back to 360 where I started. So it's kind of like a cone, but the sides are curved in. It's not straight-sided cone. Now, if you draw a representative circle on this one, this one's kind of small, might be a little harder to see. If you pick just a random point and follow it around and try to draw the radius of that circle, the radii are going to be measured horizontally. So horizontally means in the x direction. So we're just going to put an x in for the radius. That radius is somewhere between 0 and pi over 2. And as a matter of fact, we will have a circle for every single possible radius between 0 and pi over 2. So for our surface area calculation, we're integrating from 0 to pi over 2. The circumference of that circle is 2 times pi times radius. Well, that radius is a horizontal distance, so it's going to be x for the radius. And then we want to do that for every single possible circle that we could create along this arc. So we also need the length of that arc, which is 1 plus f prime of x squared, which we need to work along the side. So y prime, remember y is 2 sine x, so y prime is 2 cosine x. And then we need to square that, so we get 4 cosine squared x. This one we definitely can't do by hand yet, because we've got trig and like a polynomial algebraic piece. So we haven't really talked about mixing those two things yet. We will, though, in chapter 7. So I would probably just leave the 2 pi out, even though we're gonna end up multiplying this back in here. It makes it easier to type in the calculator if there's stuff that you can pull out, though. But when you type this in the calculator, you're gonna have to type it in as square root of 1 plus 4 parentheses cosine parentheses x close squared dx. Make sure the squared is not on the angle. Make sure the squared is being applied to the entire cosine piece. Make sure the squared is not outside of the square root. That it's just on the cosine piece, but you don't want it on the angle. We want the entire cosine value squared. So that can be sometimes tricky to type in your calculator, so just be really careful. Make sure you got a sufficient amount of parentheses. And we're going to have to just type this in the calculator. For right now, I'm going to leave the 2 pi out. You also need to make sure that you are in radian mode. Your calculator must be in radian mode in order to do this. So let's see what the calculator has to say for the integral from 0 to pi over 2 of x times the square root of 1 plus 4 cosine of x squared. So just for the integral the way I have it written now without the 2 pi, I got 2.758. And then if we go ahead and multiply the 2 pi into it, you can ask the calculator to change it to a fraction for you. It's not going to. It gave me back 2.758 something again. So I'm just going to go ahead and multiply the 2 pi into it. There's no point in leaving 2 pi times an irrational number. The only time you'd leave the pi out is if the rest of it can be written as a whole number or as a fraction. But if the other piece is a decimal and you can't help it, you might as well just go ahead and multiply all of it together. So if we multiply the 2 pi in, we get about 17.33 square units. Okay, so that's the two differences. It all just depends on how you're going to draw that representative circle, and once you draw it, whether the radius is horizontal or vertical. If the radius is vertical, you have to use y as your radius, and y, we don't want to put the letter y into this integral, because then we'd have an integral with x's and y's in it. What we do instead is, since y is equal to all of that stuff, we would put the actual function expression in there if we needed to. And if we're going around the y-axis, we see the radius is measured horizontally, which means the radius is just an x value, so we can just put an x in there.